Okay, so that was sort of the easy level ice table. Keep in mind that you will also sometimes be given initial concentrations and the equilibrium constant, which means then you'll first have to determine the reaction quotient Q to decide which direction the reaction is going to shift before continuing any calculations using your ice table. Second example. A reaction mixture at 2000 degrees Celsius initially contains a concentration of nitrogen gas of 0.200 molar and oxygen gas of 0.200 molar. Find the equilibrium concentrations of the reactants and product at this temperature. Reaction. Ice tables. Step 1. Set up known initial concentrations and equilibrium concentrations. Note, this time we're only provided with initial concentrations of our nitrogen and oxygen gases. It's understood that we don't have any of our NO to begin with. Now, an important difference in this example, we aren't given any equilibrium concentrations, so we can't right away determine which direction this is going to shift. Step 2. We're going to use our initial concentrations to calculate Q and predict the direction of the shift. So Q is the concentration of products over reactants. Plug in your initial concentration values and determine the value of Q to be 0. Now, as you compare K and Q, recognize that K is larger than Q, and therefore the reaction is going to shift to the right. Boom. An important step when you are not given equilibrium concentrations. Brings us to step 3. Represent the change in concentrations of one of the reactants or products using the variable X, and then define the changes in the other reactants and products using the stoichiometric relationship found in the balanced equation. So this time, because we're not given an equilibrium concentration, we're just going to use the variable X. Notice that my change in X for nitrogen and oxygen are each going to be minus X. We know this reaction is going to be shifting to the right, and therefore these concentrations will be decreasing. The concentration of NO is going to be increasing, so I use a positive value, but it's also positive 2x. The change here is going to be twice as much as the change of N2 or O2 as indicated by the stoichiometry in the balanced equation. Step 4. Sum each column to determine equilibrium concentrations. In this case, we're going to sum them and define them still using X. So our equilibrium concentrations of N2 and O2, 0.200 minus X, equilibrium concentration of NO, 2X. Step 5. Substitute the equilibrium concentrations into the equilibrium constant expression and solve for X. Again, equilibrium constant, concentration of products over concentration of reactants. Boom. Always write this out in terms of the species of your products and reactants in your equation. Always. Even when you're under pressure and you have to do it for time on a test. Always. Then just plug in your equilibrium concentrations that you've solved for in your ice table. Now here, we're given the value of the equilibrium constant is 0.1. So our expression is equal to 0.10. Now it just becomes a fun algebra time. Recognize that if I multiply these two quantities together, I get 0.200 minus x squared. This results in a perfect square, sort of like me. In other words, if I square each side, square root of 0.1, that's going to result on the other side of the equation of 2x over 0.200 minus x. And perfect squares are an important thing to look for. Let's keep busting out the algebra. I'm going to multiply each side by 0.200 minus x. Boom. I'm then going to distribute this square root of 0.1 throughout this quantity in parentheses. We end up with 0.063 minus the square root of 0.10 x equals 2x. I'm going to combine like terms by adding the square root of 0.10 x to each side. That gets me 0.063 equals square root of 0.10 x plus 2x. Combine further, that gets me 0.063 equals 2.3x. Divide each side by 2.3, x is equal to 0.027. True plus second square root 0.1, answer 0.063 divided by second, answer. Boom. Step 6. Substitute x into the equilibrium concentrations that we determined in step 4 to determine the actual equilibrium concentrations. Since we know now what x is, we can plug it into these equilibrium concentrations and determine what they actually are. So For nitrogen, it's going to be the initial concentration minus X, which we now know is 0.027. A quick jump to the calculator tells you that at equilibrium, the concentration of N2 is 0.173 molar. That is also true for our concentration of oxygen at equilibrium. Boom! 0.173 molar. For NO gas, recognize that we defined it as 2x, and that x is that 0.027. So at equilibrium, the concentration of NO is 0.054. Now, we've answered this question, we've determined the equilibrium concentrations. But a great final step, step 7, check your answer. Sub your equilibrium concentrations into the equilibrium constant expression and see how it compares to the original equilibrium constant value. Again, recognize how we define the equilibrium constant for this reaction. Plug in your equilibrium concentration values, which we just solved for, and determine the value of the equilibrium constant. Compare. Ding! Ding! Now, although they're not identical, considering the rounding we did with significant figures, these two match up. And also, just think about what a K value less than 1 means. Our product concentration is going to be less than our reactant concentrations. And that's what we got. Math does it for me every time.